Hey there, my amazing math community. I am thrilled to be back with yet another exciting video, and this time we're about to witness something truly extraordinary. As you know, we have covered a wide range of captivating math topics in our previous 20 videos, exploring sometimes trigonometric concepts together. But today, I have something special in store for you. And did you know that even the most challenging trigonometric equations can be conquered using a surprisingly innovative solution? So buckle up, my friends, because we are about to unravel the secrets of solving such mind-boggling equations using none other than algebra. Well, I have to say trigonometric equations also kind of algebraic equations, but yeah, we typically resort to trigonometric identities to solve such equations. But today, my goal is to resort to just simply purely algebra. So we have the following equation: cosine 2 of x plus cosine 2 of 2x minus 2 cosine of x plus cosine times cosine of 2x times cosine of 4x equals 3 over 4. So the first intuition for solving this problem is to find a relationship for cosine of 2x and 4x, replace those guys in the equation, and then come up with a final equation based on cosine cosine of x. Probably you will get some, yeah, high order equation based on cosine of x. If you, let's say, assume cosine of x is a new variable, then you have to solve that high order algebraic equation. Okay, this is one way to go about the problem. I have no idea how you can solve it that way. Perhaps there is a way, definitely, I'm sure about it. But today I want to show you something else. And that has to do with Euler formula for complex numbers. So we know that Euler formula tells us e to the power of I alpha is equal to cosine of alpha plus I. Well, let us just use x, okay? Because here alpha is basically x. So cosine of x plus I sine of x. And if I just manipulate this a bit, then I get e to the power of minus ix equals cosine of my x minus x is just x. And here I have minus I sine of x. Okay? And if I just sum these two equations, it gives me cosine of x equals 1 over 2 times e to the power of ix plus e to the power of minus ix. Okay? We know from complex numbers that e to the power of ix is a complex number in the coordinate system which is always on the unit circle. So if this is the unit circle, the absolute value of this complex number, let's call it z, is always 1. So it's always somewhere here, depending on the angle, depending on x. Let's say if this is x, then it is here. So what I am going to do is to take e to the power of ix as z, like here, and just replace it. So z for me is a new variable. Then I can say cosine of x equals 1 over 2 times z plus z to the power of minus 1, which is basically 1 over z. I hope you agree with me on that. Okay? So I found the formula for cosine of x based on a new complex number, and this is what I'm going to use in these equations. However, I have to do something about cosine of 2x and cosine of 4x. Okay? So what do I do about those guys? Obviously, I can also use the same formula like here, put instead of x, just put cosine of 2x, and then I will get something like e to the power of I2x Well, that is also one way. So actually, maybe I can do that. So let's say cosine of 2x equals 1 over 2 e to the power of I2x. Well, initially, to be honest with you, I solved the problem by finding an expression for cosine of 2x based on cosine of x. But as I was trying to explain this video to you, just this new solution came to my mind. And I said, well, why not trying it out? Okay. So yeah, guys, sometimes when I'm solving a problem for you, yeah, new solutions come to my mind during the solving process. So this is e to the power of minus I2x. And well, this is nothing but 1 over 2 times, well, what is e to the power of ix? This is z. So I can say, well, this is z2 plus z to the power of minus 2, which is basically 1 over z2. Okay. So I got that. And then cosine of 4x, then this is also equal to 1 over 2 times e to the power of I 4x plus e to the power of minus I 4x. But again, similarly, this is equal to 1 over 2 times z4 plus 1 over z4. Perfect. You see how beautifully it can be simplified? So now let's go back to this equation here, and we just simply, replace cosine of x, 2x, and 4x with these values. If I wanted to use, just as a note, if I wanted to use trigonometric identities, it would be a little bit more complicated because now I had to say, well, cosine of 2x was 2 cosine 2 of x minus 1, and then cosine of 4x was 2 cosine 2 of 2x, and this minus 1, and then I had to replace cosine of 2x with this guy here. You can imagine it would be a little bit more complicated, but using this Euler formula here, it just makes things really simple. Okay, now let's go with our simple solution. Now next I'm going to just replace these guys. So I have first cosine 2 of x. So I derived cosine of x to be this, and then I have cosine 2 of x, which is basically, let's say, 1 over 2 times z plus 1 over z, okay, to the power of 2, plus cosine 2 of 2x, which is basically 1 over 2 times z2 here, plus 1 over z2 to the power of 2. And then I have minus 2 times, those values. Then I have minus 2 times cosine of 2x. Am I right? Yes. No, sorry, cosine of x. So then I have minus 2 times 1 over 2 times z plus 1 over z. And then I have cosine of 2x, which is basically 1 over 2 z2 plus 1 over z2. This is times cosine of 4x, which is basically 1 over 2 times z4 plus 1 over z4. Okay, this is equal to 3 over 4. Okay, so now here, I want to get rid of this 1 over 2. You know, in this first term, it creates a term 1 over 4, here the same, and also here the same, because this is 1 over 2, 1 over 2, 1 over 2. This 2 is cancelled, so again, I have 1 over 4. And then I just can multiply both sides by 4. Then I get rid of that, and also I get rid of this 4 here, okay? On the right side. Then what I get is the following. So z plus 1 over z to the power of 2 plus z2 plus 1 over z2 to the power of 2 minus z plus 1 over z times z2 plus 1 over z2 times z4 plus 1 over z4 equals 3. Okay, guys, hopefully you will not confuse this 3 with z. Sorry if it looks a little bit weird, my z. So next, again, I want to simplify this further. So if I multiply both sides of the equation, look at z here, I have 1z, 1z2, and 1z4. So the sum of the powers is z7. I will multiply both sides by z7, okay? So for the first term, z7 equals z2 or z5 times z2. And I take z2 inside the parentheses, so power 2 will disappear. And for the second term here, I will have z7 equals z3 times z4, and then z4 goes inside the parentheses because of the power 2. Then I basically get z2, and for the for the third term, I will have z7 equals z times z2 times z4. I'm going to use it this way. So let's see what it generates. For the first part, then I get z5 times z2 plus 1 to the power of 2 plus z3 times z4 plus 1 to the power of 2 minus z2 plus 1 times z4 plus 1 times z8 plus 1. This is equal to 3z to the power of 7 because we multiplied both sides of the equation by z7. And now I have to simplify this further. The first two terms can easily be simplified, and so also the third term. But before actually doing that, let us just first calculate this. This is z12 plus z8 plus z4 plus 1. It makes it easier in the next step. So then this guy gives me, I have z9 plus 2z7 plus z5 here. And then for the second one, I have z8, 11, and then 2z7 plus z3. And then I get z2 plus 1 times this guy here, which basically generates z14 minus z10 minus z6 minus z2, and then maybe I have to come here, minus z12 minus z8, then I have minus z4 minus 1 equals 3z7. Okay guys, next I have to simplify this further, and I have minus z14 here. What is the next biggest power? Then I have minus z12, and then I have z11 here. Then I have z10 here, so I have minus z10, and then 9 here plus z9, and then I have z8 here. Are you noting that the signs kind of are alternating between plus and minus? Keep this in mind because it can be helpful later. And okay, I took care of z8, and then I have to take care of z7. So I have 2z7 here, I have 2z7 here, and then I have 3z7 also here. So both sides, if I consider both sides, then I get here plus z7, and z6 here minus z6, okay, plus z5, which is here, then minus z4 here, and plus z3 here, okay, and minus z2. Okay, I have to delete this. So minus, well, let's come on the next line, minus z2 here, minus 1 equals 0. Okay, let's ponder over this equation a little bit. So I have all the powers except for 2 power, which is z13 and z. Okay, if I just add those 2 powers, taking into account the fact that the signs of these terms are alternating between plus and minus, I want to add the right sign and then subtract the same powers. So I get here, so let's say I also factorize this minus here, so I get minus z14. Let's just add a minus z13 here. I'm going to take care of it later by subtracting it. Then I get plus z12 minus z11. I'm not going to write it all. And then it will be basically all the way to this guy here, so which is basically, I think it will be plus 1, and then here I have minus z, probably, okay? So this is this, and then I have added two terms here. One is basically this guy, and one is this guy. Both of them are positive because of this negative sign here. So I'm going to just subtract them. So minus, then I get basically minus z to the power of 13 plus z equals 0. So guys, if you have any doubt about these terms, please feel free to verify it on yourself, but this is correct, okay? But the first term here is very interesting. It reminds you of a famous identity, which is basically if you have something like z 4, let's say, plus 1, this can be written as, or sorry, 4 is not the case. If the power is odd, this can be written as z plus 1 times z2, sorry, z4 minus z3 plus z2 minus z plus 1, right? Whenever the power here is odd, in general, z to the power of n plus 1 can be written this way: z times z plus 1 times z n minus 1 minus z to the power of n minus 2 plus all the way to 1 here. So if I just look at that, it sounds like n for me is 15. Then I can actually simplify that guy first in the first term. So let's go back to the equation here. Then I get minus z to the power of 15 plus 1 over z plus 1. This is just nothing but this guy here. Again, feel free to verify these identities. I don't want to get into them for this problem. And then here I get minus z times, well, let's say, let's just keep it that way, minus z13 plus z equals 0, okay? And now next, I'm going to multiply, well, you can imagine actually this minus also, you can get rid of it by just multiplying both sides by minus. So now I'm going to multiply both sides again by z plus 1. So if we do that, we get z 15 here plus 1 plus z 14 plus z2 plus z13 plus z equals 0. Okay. So now again we have to simplify this. So now what I'm gonna do, just take a look at these guys here. 1 plus z2, and then I get, let's just write those guys next to each other. Then I have 1 plus z plus z2. We have come a very long way. And then here to this simplified equation, as a matter of fact. Here, if I just take care of these three guys by factorizing z13, then I get z13 times z2 plus z plus 1. Perfect. So I managed to produce the same factor. This is equal to 0, and then I get z2 plus z plus 1 times z13 plus 1. This is equal to 0. So guess what, guys? Whenever I have the multiplication of two parentheses set equal to 0, then both can be basically 0. So once I am gonna take the first one, so z2 plus z plus 1 equals 0. and I'm gonna use the formula for quadratic equation, then I get z equals -1 plus minus square root of 1 minus 4, which is basically minus 3 over 2, and that gives me minus 1 over 2 plus minus I square root of 3 over 2. So you guys remember what z was. Z was e to the power of ix, and this was nothing but cosine of x plus I sine of x. So I was supposed to find x, right? So if I look at these values which I derived right now, so one root will be minus 1 over 2 plus I square root of 3 over 2. But you remember actually z was on the unit circle in the complex plane. So if this is the complex plane and this is the unit circle. And by the way, look at this z1. So you remember this is cosine of x and this is sine of x. And cosine is negative, sine is positive. Where can it happen? It can happen only here. And if you pay attention to these values, then you just find out that actually x should be 2 pi over 3, because cosine of 2 pi over 3 is minus 1 over 2, and sine of it is square root of 3 over 2. And also it just corresponds with the right signs, minus and plus. So, well, then x should be 2 pi over 3, but because I have a trigonometric function, again, you can add general terms. So 1x for me will be, we can call it x1. X1 equals 2 pi over 3 plus 2kp, okay? And k belongs to z. So guys, we found one answer here. And let's look at z2. So z2 is minus 1 over 2 minus I square root of 3 over 2. And again, looking at the complex plane here, it can happen only in this area where both cosine and sine are negative, which means either it is pi plus pi over 3, which is 4 pi over 3, or you can also say minus 2, come the other way, this direction, minus 2 pi over 3. So then x2 will be minus 2 pi over 3 plus 2kp, where basically k again belongs to integers. So this is another root for our equation. But we had another term here as well, and that is the interesting part. So let's look at this as well. So then I get z to the power of 13, z to the power of 13 plus 1 or equals 0, or let's say z to the power of 13 equals minus 1, which is nothing but e to the power of ip. Okay, but z was also e to the power of ix, so it means e to the power of I 13x equals e to the power of ip. So what does it suggest? Well, this can also be generally written as e to the power of I times p plus 2kp, where k belongs again to integer values. So it just suggests that these two angles generally all the same, and that is pi plus 2kp, and that means the next solution will be, which is actually the interesting solution, will be pi over 13 plus 2kp over 13, where k again belongs to z values. Okay, so we got the solutions. Congratulations, my fellow math enthusiasts. So we have conquered this formidable trigonometric equation with this innovative approach, which is basically rooted in algebra. I'm incredibly grateful for your unwavering support for my videos, in the comment section, your likes, and all the rest of it. If you found this video valuable and enjoyed the thrill of solving this complex trigonometric equation, I kindly ask you to show your appreciation by smashing that like button and subscribing to my channel. By doing so, you'll ensure that you won't miss out on the exciting equations, because I promise you I have many exciting equations and I would love to share with you my solutions. And sometimes the solutions just come to my mind, new ones, as I solve the problems. So you will not miss out on those exciting equations. And thank you very much for being part of this incredible journey. And I promise you more challenges await us in the future. Stay curious, keep pushing the boundaries, and let's continue to unlock the secrets of mathematics together.